Hi everyone, my name is Pranav and I'm going to introduce you to Parallelized here in my desktop project. My lectures are Viral and Shashi. So let's get started. The goal of my desktop project is to develop a package that will address the graph processing needs of data scientists. Some of the use cases that I'm trying to address are vertex and edge metadata, vertex labeling, SQL-like queries for graphs, and parallelized graph processing. So coming about the architecture, each graph has three separate components: an adjacency module which will store edges, a property module which will store metadata, and a label module which will resolve vertex labels. There can be several implementations of modules, which is an abstract case. So you can mix and match these implementations and get different graph structures. So the adjacency module is the most important component of the graph. There will be two separate implementations: the light graph AM, refer to the existing light graph .jl library, as well as sparse matrix AM, which will use the sparse matrix CSV data structure to store edges. So let me demonstrate the graph behavior in Parallelized. So we can create a graph with 100 vertices and 1000 edges in a straightforward manner by just using the constructor to construct a random graph. You can query the size of the graph, add a vertex to the graph, add an edge to the graph, get a list of vertices and edges connected to the adjacency, as well as construct subgraphs. Here I am running a BFS from vertex 1 and constructing a subgraph with all vertices reachable from vertex 1. So basically you have all the algorithms that you come to expect from a regular graph processing library. So most useful graphs are representations of real-world objects, and these objects often have metadata attached. A social network is an example where a vertex is a person and edges are relationships between people. As you can see, vertex and edges have attributes that can be attached to it. So what data structure would be used to store metadata? So far I've experimented with Julia dictionaries pointing to sparse arrays pointing to dictionaries, and n-dimensional sparse arrays that can be found in Julia computing many sparse data library. The dictionary of arrays, of course, was the most scalable. It also kept a number of allocations in text. So I guess I'm going to go through with that. So let me give you an example of the graph API and Mozilla. So you can attach properties to all vertices in the graph by just passing a function. Paper is a very handy package with a large data set from using vector. So I'm giving every vertex its name, an age, and an occupation. Similarly, for edges, you can here I'm coloring edges with the red for green. You can also attach a sum of the incident vertices to each edge. You can query every vertex in the graph. Here I'm fetching all properties attached to vertex 1. Likewise for edges, here the edge is 1 is 60. Most graph libraries force users to use the internally used indices, which are often integers, and when you're using social network, the vertex is a person, so it's pretty inconvenient to refer them using an index. So Parallelized will support vertex labeling using arbitrary Julia types. So these types will be these labels will be accessible only from the query system. Develop a query model where most of the edge and metadata can be extracted using getIndex semantics. Parallelized will also provide smart filters which will help you construct subgraphs and extract data from the graph. For example, here I am setting the label of every vertex to its name field so as to avoid redundancy in data. This command fetches all vertices in the graph. You can fetch all edges in the graph. Able is the first guy in the social matrix generated. So GeoAble gives you all properties attached to labels. Similarly, you can get all edges starting from labels, which is a bunch of people. The smart filter. So say you want to fetch all senior citizens in the graph, then v.age greater than or equal to 65 will give you a list of all people in the graph over 65. Similarly, if you want all red edges in the graph, you can get a list of all edges which are red. Say you want to construct a graph with only senior citizens and only green edges. The filter query can be used to construct such a subgraph. So basically, you can change many different queries and get a root subgraph. So over the next few months, I plan to add the following things: extend the existing graph APIs, implement faster and lighter property models, which will be quite important, smarter and insightful queries as well, and more integration of the existing graph library, which is like graph purchase, we can use all the algorithms from there, and parallel processing with compute framework, which is kind of a misnomer in parallel graph purchase. So thank you.